chemistry land. We talked about thermodynamics, and we said in order for a reaction to occur, it has to be both kinetically favorable and thermodynamically favorable. Last time, we introduced disorder. What do we call a measure of disorder? Entropy, abbreviated with an S. Okay? We said, for example, or let's see if you remember. This is a super smart class, so of course you're going to remember. Let's say, for example, that iodine is undergoing sublimation. They're still on the ties. Iodine is undergoing sublimation. Is this reaction illustrating order or disorder? Disorder. And so delta S in this case would be positive or negative? Positive. You got it. All right? Also, if that concept in regard to order or disorder is a little confusing to you, I did want to re-illustrate this. For example, if you had ice, the water molecules would be vibrating in a fixed position, sort of like you guys sitting at your desks right now. You want to be little jumping beans, so some of you just keep moving and moving. Some of you feel the need to hold hands. We'll get into that later. I don't know if you're illustrating covalent bonding or intermolecular forces, whatever rocks your world. Here's water in the liquid state. You can see a little more disordered. And then finally, water in the gaseous state. This would be like water vapor in the atmosphere. This is perfect for Florida because this is what causes beautiful curly hair. So you can see the gas molecules moving around very, very quickly. There's very little order there. So that's highly disordered. So sublimation, you will recall, is showing disorder, and that would be positive entropy. Disorder is a good thing. What we're going to do today is link entropy, enthalpy, and temperature to determine whether a reaction is thermodynamically favorable. And I also want to make sure that you're okay here. We did this last time, but a little bit of review goes a long way. You should recall, you have this in your notes already, that H is enthalpy. When the change in enthalpy is positive, the reaction is endo or exothermic. Endo, heat is being absorbed by the system from the surroundings. When the change in enthalpy is negative, then the reaction is exothermic, in which the system is losing heat to the surroundings, or releasing heat to the surroundings is probably a better way to indicate. So that's the change in enthalpy. Remember, in regard to delta S, the change in entropy, when positive, you have disorder. When negative, you have order. We're going to take the change in enthalpy, the change in entropy, and the temperature, and we are going to link these three concepts together to determine whether a reaction is thermodynamically favorable. That is, does the reaction occur without any assistance? And that is what is in your notes. Three factors must be considered. We mentioned enthalpy, H, entropy, S, and temperature. Gibbs free energy, abbreviated with a G for Gibbs, measures the energy available to do work. And that's what's going to determine whether the reaction is thermodynamically favorable. There are 2 video links there that you are welcome to watch. If maybe, actually this is a very long period, so we could take some time at the end to watch if it's going to be helpful to you. Now, Gibbs free energy, abbreviated G, like enthalpy, like entropy, is a state function. And that means it begins only on the beginning and the end. So you can calculate delta G for a reaction by doing the sum of the products delta G's of formation minus the sum of the reactants delta G's of formation. The same type of question that you saw on your quiz, the very last question. So when you calculated the change in enthalpy for a reaction, you used these quantities. If you want to calculate the change in Gibbs free energy for a reaction, you could use their delta G's of formation, which are shown in this second column here. That's one way to calculate delta G for a reaction. We're going to do it a little bit differently. We're going to calculate the change in Gibbs free energy under standard conditions, 1 atmosphere of pressure, 25 degrees Celsius. Delta H, the change in enthalpy, minus the temperature, minus the change in entropy. Couple things you need to remember here to have great success with this type of problem, which most of the kids find to be extremely simplistic. So delta G is equal to delta H minus T delta S. Couple things you have to be very careful of. Delta H will be in kilojoules per mole or kilojoules. Temperature must be in Kelvin. You most likely will be given degrees Celsius. You will need to convert to Kelvin by adding 273.15. In regard to delta S, this is going to need to be in kilojoules per mole Kelvin, and it most likely will be given in joules per mole Kelvin or joules per Kelvin, and you will need to do a conversion there. So watching the units will be critical, and I'll point that out as we walk through our examples. Your units of delta G then will be kilojoule per mole or kilojoule. The other thing about delta G is delta G is the change in Gibbs free energy, and that's going to measure the energy available to do work. When delta G is negative, we say that the reaction is thermodynamically favorable. When delta G is positive, the reaction is thermodynamically unfavorable. Another word for thermodynamically favorable is spontaneous, but the newer textbooks are moving away from spontaneous and toward thermodynamically favorable. If it's thermodynamically unfavorable, we say it's non-spontaneous. And you'll see both nomenclature in your notes, etc. I tried to keep both for right now until a solid change is made. Right now it's still in the transition phase. So when you calculate delta G, you can determine whether the reaction is or is not thermodynamically favorable. Sometimes you don't have to calculate delta G, you can analyze the enthalpy and the entropy and make a determination, and I'll show you how to do it all different ways today. So for all thermodynamically favorable reactions, delta G is negative, and because you can do products minus reactants for delta G of the reaction to be negative, this term would be less than that term, similar to the way you would do the change in enthalpy. We're going to walk through two examples to calculate delta G and then determine if the reaction is thermodynamically favorable and why. And then we're just going to go over some analysis of the delta G equals delta H minus T delta S formula, and that will really just depend on your understanding of positive and negative numbers, which should be very, very strong. Let's walk through the first example together, all the tricks, then the second one. So you are generating titanium 4 chloride and oxygen gas from titanium 4 oxide and chlorine gas. The delta H is given as 140.5 kilojoules per mole. I'm going to rewrite that on my sheet so you can see all of the conversions that we need to do. So delta H is equal to 140.5 kilojoules per mole. Is that endo or exothermic? Endo. No. Delta S is equal to negative 38.9 joules per mole Kelvin. Order or disorder? Order. And the temperature is 25 degrees Celsius. We want to calculate delta G, and then we want to determine if the reaction is thermodynamically favorable and why. I don't foresee you having any issues here as long as you plug quantities into equations. If you've got your units, it'll drive you home. So delta G is equal to delta H minus T delta S. We've got 140.5 kilojoules per mole. The temperature must be in Kelvin. We already know how to do that. And delta S has to be converted to kilojoules per mole Kelvin, either by dividing by 1,000 or moving the decimal 3 to the left. Then it's just a plug and chug. You actually don't need any parentheses in your calculator. A scientific calculator will take care of all order of operations. On your phones, if you're doing a lot of calculations on your phones for practice, I would recommend installing a scientific calculator. So we've got 152.1 kilojoules per mole. The Kelvin canceled. In regard to sig figs, I typically look at my delta H and however many decimal places it is, I usually carry it. It doesn't always work, but I won't mark it wrong if you do it that way. So delta G here is 152.1 kilojoules per mole. So is this reaction thermodynamically favorable? No. How come? Exactly. but don't write it. Not the reaction either. Some of you did that on the quiz. The reaction is thermodynamically unfavorable because delta G for the reaction is positive. Easy peasy? You got this, Nick? The second example is a little more challenging, but nothing you can't handle. I'm going to write the second one on paper so we can follow along. In the second example, we have the combustion of propane They don't give us the delta H. The delta S is 650.2 joules per Kelvin, and the temperature is 25 degrees Celsius. So before we can determine delta G, we first have to determine delta H. So you will need the delta H's of formation just like you did on your quiz. And I think these are all on the back of your periodic table. So just like we did the other day, propane has a delta H of formation of 104.7 kilojoules per mole. Oxygen, of course, is 0. Carbon dioxide is negative 393.5 kilojoules per mole, which I have the unit here so I don't have to keep writing it. And then water in the gaseous state, be careful, negative 241.82 kilojoules per mole. So how do we calculate the delta H of the reaction first? Yep.
You do the sum of the products minus the sum of the reactants?
In terms of their delta H is taking coefficients. You got it. So you have 3 moles of carbon dioxide times its delta H of formation. And this is kilojoules, little k, capital J. A couple kids wrote kilograms on the quiz. Don't do that. 4 moles of water, negative 241.82 kilojoules per mole, close, minus, just like you did on the quiz, 1 mole of propane, negative 104.7 kilojoules. And even if it's 1 mole, you should indicate it because that's what gets the units to cancel in terms of moles. And then, if it's a 0, I typically don't put it in, but whatever rocks your world is fine. And I am seeing some calculation errors on quizzes. Make sure you're comfortable plugging quantities into your calculator. The more practice you do, the more apt you will be, or the more likely to get it correct. The delta H for the reaction is negative 2043.1 kilojoules. So that's the first piece right there. Is that an endo or exothermic reaction? That's exo, and I do want to point out it's exothermic because the change in enthalpy for the reaction is negative. Please don't write the reactions negative. Please don't write it's negative, and it's not the delta H of formation. Okay, be careful there. They gave us delta S in joules per Kelvin, so what do we need to do? Convert it to kilojoules, move the decimal 3 to the left. So we've got 0.6502 kilojoules per Kelvin. Is that order or disorder? Disorder with positive entropy. And the temperature in Kelvin is 298.15. Okay. Now we're ready to do the second part. What's our formula to determine delta G? Delta H minus T delta S. Negative 2043.1 kilojoules minus 298.5 Kelvin times 0.6502 joules per Kelvin. The Kelvin cancels. And we have negative 2,237.0. This should be a kilojoules. I put the correct number in, but I had the unit cockeyed. Do you see it there? I just wrote it wrong. And that's kilojoules. So the reaction here is what? Is thermodynamically favorable because delta G for the reaction is negative. And I want to just do a little bit analysis of that. You guys are very strong in math, and this is like going to be like 7th grade math, so it should be golden. Questions here? And you'll see on your classwork number 13 has several problems like this to really hammer the point home. Before I let you go, I do want to go over the rules in that table. It's all in your notes. I'm going to do it in a very simplistic fashion. You will see here that this exothermic reaction that favored disorder resulted in a thermodynamically favorable reaction. Any reaction that is both exothermic and illustrates disorder will always be thermodynamically favorable. For example, for this equation, an exothermic reaction has a negative delta H. I know some of you are very concerned with this calculation. We have a lot of time this period, and I'd like to explain this to you. It's really a good analytical tool. If you're struggling with the calculation, I promise we will clarify it in a few minutes. An exothermic reaction has a negative delta H. A reaction that favors disorder has a positive delta S. A negative minus a positive always, always, always gives rise to a negative, and a negative delta G means the reaction is thermodynamically favorable. So an exothermic reaction that illustrates disorder will always be thermodynamically favorable. And that's what you saw here. On the flip side of that, an endothermic reaction with a positive delta H that illustrates order with a negative delta S, a positive minus a negative will always have a positive delta G and therefore be thermodynamically unfavorable. And that's what you saw in the first example. In the first example here, we had an endothermic reaction that illustrated order. An endothermic reaction that illustrates order will always have a positive delta G and be thermodynamically unfavorable. And that's what you'll see in the first two rules. Temperature plays a factor in the following way. Let's say, for example, that you have an exothermic reaction and order. And let's say we want thermodynamic favorability. What's the only way that delta G will be negative with an exothermic reaction that favors order?
If the exothermic reaction is larger.
If this is more negative
Yeah.
than that. So you can get a thermodynamically favorable reaction if the enthalpy term predominates, and you can get that at low temperature. Because at low temperature, entropy won't be as critical. And then you can have a thermodynamically favorable reaction. Similarly, if you want a thermodynamically favorable reaction, when you have an endothermic reaction that favors disorder, you can achieve that if this term is larger than this. So the entropy term will predominate at high temperature. That can be a little bit tricky. An exothermic reaction that favors disorder is the perfect vehicle for thermodynamic favorability. The opposites will never generate thermodynamic favorability. An exothermic reaction that illustrates order can be thermodynamically favorable if this term is sort of suppressed, which you could do at very low temperature. And an endothermic reaction that illustrates disorder helps drive thermodynamic favorability. So here you want this term to predominate, and it will do so at high temperature. This can be a little tricky, and you'll see some of that in your notes as well as in your classwork. So for today, thermodynamic favorability is determined by delta G. If delta G is negative, the reaction is thermodynamically favorable. If it's positive, it's not. Thermodynamic favorability depends on enthalpy, temperature, and entropy. Questions here? Little practice and you'll drive it? All right. In your classwork, which you can work on for the rest of the period, you should be able to do everything that's left. So 13 through 16. There are extensive explanations provided in 15 and 16 to really make sure that you're understanding. But this is the classwork you want to work on. I would think you could easily finish it in the more than the half an hour that remains in class today. Tomorrow and the following day we've got a lab. Your test is until Tuesday. Please don't wait until the last minute to study. Many of you are celebrating a holiday on Sunday, so please use Sunday for your holiday. Don't wait until Monday night to do all the classwork. That doesn't go well. Finish your classwork off today and tomorrow, and this way you can just review it over the weekend in preparation for your Thermo test. I'll get your quizzes back to you so you can look them over. You already saw your grades. Questions here? We've got it? Okay.